All right, so like I mentioned, today we're starting chapter 8, which is going to be on time series analysis and specifically looking at transforms. We're going to start by talking about what inner products are and of functions and vectors. We'll then go through a Fourier series, Fourier transform, discrete Fourier transform, and we'll also look at what frequency response functions are, and eventually we'll end at the FFT. And if we have time, we'll start worksheet 4 today. If not, we'll just do it when we come back from fall break next week. All right, so we're going to start by just talking about what inner products are for both vectors and functions. And we're going to consider both continuous and discrete transforms because they're very much related to each other. And by, you really need to understand both to understand what's going on. And that's why we're going to do both vectors and functions. And so in general, the inner product of two functions is comparable to the dot product of two vectors. And we're going to define it for two functions, for f of t and g of t for t on some interval a to b. In that case, we can define our inner product to be the following. We're going to use triangular brackets to represent this inner product. We'll say that this is f of t, comma g of t, so the inner product of f of t and g of t, and this is equal to then the integral from a to b of f of t times g over bar of t dt, where this over bar indicates the complex conjugate. And what we just defined here is known as the Hermitian inner product. So then let's imagine that we go ahead and we sample these continuous functions and we get two discrete vectors. First we have f, which is now a vector equal to some f0, f1, all the way up to some fn, and then g, it also becomes a vector equal to the collection of points g0, g1, all the way up to gn. In this case, the inner product is then going to be defined as, we'll still use those triangular braces, but we'll have f underbar, g underbar. This inner product is defined now as a summation from n equals 0 to n of f underbar n times g underbar n, also with an overbar. So it's still the complex conjugate of g, which is equal to the sum from n equals 0 to big N of f of n times g over bar of n. And one thing I need to correct here is we need to get rid of these underbars because we're multiplying components, not multiplying vectors. Pure multiplication of vectors doesn't make sense. You have to define what that is and what multiplication you're using. Okay, so the unfortunate thing about equation 4 is that its magnitude will increase, or may increase at least, as you add more and more data points. And to avoid this, we're going to normalize by multiplying by, let's say, delta. We'll just use delta x is equal to b minus a divided by big N minus 1, such that our inner product becomes the inner product between f and g is equal to the quantity b minus a divided by n minus 1 times that summation from n equals 0 to big N of f of n g of n. it is the duration. So if you recall, we sampled our continuous vectors. First off, f of t and g of t lived on the domain t from a to b. And so in that case, this is just the width of, well, the duration divided by the number of samples minus 1.
So here are we projecting f on g or g on f?
We also need a complex there. So in this case, we are projecting, I think, f onto g in this case.
So it's important to recognize which one, to know which one
Yeah.
first and which one second.
Right. Yeah, we are projecting f onto g. Yeah.
What do those the square brackets mean?
The triangular brackets.
No, in the summation, f of the square brackets n, what is it?
So these are discrete signals,
Okay.
meaning that they have they're sampled at discrete times.
Okay.
Which is what we discussed on Tuesday. So when we did looking at continuous functions of time, like f of t and g of t, we're using these parentheses. When we're looking at discrete signals, which are, again, some type of collection of points, which could be infinite in either direction or one direction, or both, we use square brackets. Okay, so in the limit of n goes to infinity, this delta x is going to go to 0, such that the equation we have in 6 will end up converging to that integral inner product that we defined in equation 1. So if you could sample with infinite precision or at an infinite rate, you would end up back with this continuous integral that we started with. Okay, we can also define what's known as a norm for functions. And in this case, we're going to use 2 double lines to represent our norm. And in this case, we're going to be looking at what's known as the L2 norm. So we're going to just put a 2 in a subscript there. This is equal to the inner product of f. Well, it's equal to the square root of the inner product of f with itself, which is then equal to the integral from a to b of f of t times f over bar t dt, all of that raised to the 1/2 power. And like I said, this is known as the L2 norm, written as L squared, but read as L2. You can define a similar norm for discrete systems or discrete signals. And this is not the only norm that exists. There are many, many different types of norms that people use. We are not going to study them in general. We're just giving a general overview of this stuff. And really what we want to get out of this is what Mohammed brought up earlier, is that this key benefit of the inner product is that it can be used to project functions onto new coordinate systems, provided that those coordinate systems are defined by some set of orthogonal basis function or orthogonal basis vectors as well. And this is, again, equivalent to projecting a vector into another set of directions or coordinates. And this is exactly what is done in Fourier analysis with Fourier series, and this is what we're now going to talk about is Fourier series. And we're on our way to getting towards a Fourier transform, and then we'll go from there. All right, so we're going to consider a periodic piecewise smooth function, f of t. And then, given such a function, then the fundamental result of Fourier theory is that we can expand this function f of t into an infinite series composed of sines and cosines, i.e. a Fourier series. I think probably everyone has seen this before, but we're just going to go over it so that everyone's on the same baseline. So we're going to assume here that f of t, first we're just going to assume that it's 2 pi periodic. And then if we do that, we can then expand f of t into an infinite series of a0 over 2 plus the summation from n equals 1 to infinity of an times the cosine of nt plus bn times the sine of nt and here an is equal to 1 over pi times the integral from, in this case, minus pi to pi times f of t times the cosine of nt dt. I'll lower that. And then bn is equal to 1 over pi, the integral from minus pi to pi of f of t times the sine of n of t dt. And here, these are the normalized inner products. So this is that projection onto the orthogonal bases composed of these cosines and sines.
Why do you use the integral limits from minus pi to pi? I mean, you can use 0 to 2 pi, right?
Sure. Yeah.
But it depends on the signal, right?
Well, I mean, you can always shift the signal in time.
Should-
Yeah. You don't get hung too much up on the details because we're going to do like Fourier transforms today and maybe Thursday next week, but we're not going to do a lot with them because they're not very applicable to nonlinear systems. And so you won't really get a homework on any of this, on this stuff at least. And I assume most of you have seen this before somewhere as well.
So we don't use FFTs on nonlinear systems?
I mean, you can, but we will see later why it's not very helpful. FFTs are sort of like the standard approach, not because they're good, but just because they're standard from linear systems. And that's just a whole, I mean, people are familiar and very familiar and used to using FFTs from linear systems. And when they go to apply it to a nonlinear system, it doesn't work, but that's what they are used to. And so we're going to graduate and use more sophisticated and better tools to study these. But yeah, so you could use 0 to 2 pi. We're about to deal with a t periodic function and so forth. And you can do a whole bunch of other things you want with this types of series as well. Okay. So in that case, we can say that this Fourier series is resulting from projecting f onto that orthogonal basis, which is defined as, let's switch to red. It's defined as the cosine n of t, nt, and sine of nt. For n within 0, or n in the domain of 0 to infinity. And actually, hold on. We should not say that. N is a set of integers. It's not just any number with 0 to infinity. But it's, yes, it's an infinite set of integers. Let me correct that. Okay, so now for a t periodic, capital T periodic function on the interval from 0 to capital T, the Fourier series is simply going to be a0 divided by 2 plus the infinite sum from n equals 1 to infinity of here an times the cosine of 2 pi n over big T, all that multiplied by t, by lowercase t, plus bn times the sine of 2 pi n over big T times lowercase t. Okay, here an is equal to 2 divided by big T times the integral from 0 to big T. That's the interval of that we're considering this function. The integral of f of t times cosine of 2 pi n over big T times little t dt, and then similar, bn is 2 over big T times the integral from 0 to t of f of t times the sine of 2 pi n over big T times t dt. Okay, so we will not use the Fourier series to do any real analysis of systems. We're just using it as a stepping stone to get to the Fourier transform, which we're then going to use as a way to look at, first off, frequency response functions of linear systems, and then we're going to go into discrete and fast Fourier transforms. All right, so let's consider the Fourier series of f on the interval, in this case, from minus t to positive big T. And in this case, we can say that the Fourier series is going to be a 0 over 2 plus summation from n equals 1 to infinity of an times the cosine. In this case, it's just n pi divided by big T, all that times little t plus bn times the sine of n pi over big T times t. And an and bn are defined similar to what we saw previously. We're not going to write them out this time. Instead, we're going to convert this into a complex form, and we can say that this is equivalent to the infinite sum from n equals minus infinity to infinity of some Cn times e to the j n pi divided by big T multiplied by t here, where j here is our imaginary constant. It is not an integer. And in this case, the Cn is equal to 1 over 2 times big T times the integral from minus big T to big T of f of lowercase t times e to the minus jn pi over big T times t dt. And we are going to call this exponential term here, we're going to call that psi sub n of t. Okay, so currently f of t is represented by a sum of sines and cosines at discrete frequencies, and these discrete frequencies are some omega n equal to, in this case it's just n pi, oh wow, n pi over big T. In this case for n goes from minus 2, minus 1, 0, 1, 2. In this case, it stretches in both directions to infinity. Okay, so we are going to define omega to be equal to n pi over t, such that our delta omega, which is just the difference between iterations or successive values of n, is just equal to pi over big T. We're then going to take the limit as big T goes to infinity. As a result of that, delta omega is going to go to 0, and we'll end up with the following. We'll get that the limit and we're going to write it as delta omega goes to 0. The limit of the sum from n equals minus infinity to infinity of delta omega over 2 pi times the integral from minus pi over delta omega to pi over delta omega of f of tau times e to the minus j and delta omega times tau d tau, all of that multiplied by e to the j n delta omega t, and everything stored in that square bracket is the inner product between f of t and that psi n of t. Oh, sorry. Okay, so under the limit, that inner product becomes what's known as the Fourier transform of the function f of t, which we will define as being, we're going to use hats here. So f hat of omega, this is equal to the Fourier transform, which we'll use a script f to represent, and then curly braces acting on f of t. And this is defined to be the integral from minus infinity to infinity of f of t times e to the minus j omega t dt. And then we can define the inverse Fourier transform to be, just move that up a little. So it'll be that script f inversed acting on f hat omega, in this case defined as 1 over 2 pi times the integral from minus infinity to infinity of f hat of omega times e to the j omega t d omega in this case. And you might see the 2 pi used in the definition of the Fourier transform, the 1 over 2 pi there. You might see 1 over pi on each of them. Different books and different approaches might choose to put that 1 over 2 pi somewhere else. All right, we're going to go through some properties of the Fourier transforms, and then we're going to talk about what are known as frequency response functions, which comes from studying vibrations of structures. And then we'll do some examples. All right, so first, the Fourier transform is linear. It obeys linearity, meaning that if if we want to take the Fourier transform of the function alpha times f of t plus beta times g of t, we can pull out the constants alpha and beta, and then apply the Fourier transform separately to each of the two functions inside there. So we'll get alpha times the Fourier transform of f of t plus beta times the Fourier transform of g of t such that we can just simply apply the Fourier transform to the components that depend on time, pull out constants, and then add them all together later. The second one is what's known as a time shift, which we saw on Tuesday. So if we want to compute the Fourier transform of the function f of t minus a, this is equal to e to the minus 2 pi j times a omega multiplied by the Fourier transform of f of t. We also have what's known as scaling, or a scaling property, which is the equivalent of decimation or interpolation that we saw for discrete signals. And in this case, we'll just say that the Fourier transform of f of ct, where c could be greater or less than 1, so it could be a decimation approach. This is equal to 1 over c times f hat of omega over c. So by either decimating or interpolating some continuous function, we end up scaling both the amplitude as well as the frequency domain as well, so that it's equivalent to shifting up or down in the frequency domain. Okay, the really important thing is what happens when you apply Fourier transform to derivatives. And in this case, we'll look at first derivative and then we'll look at a second. So the Fourier transform of d by dt of f of t, so the first derivative, this is simply equal to j omega times the Fourier transform of f of t, or j omega times f hat of omega. For the second derivative, we're going to have Fourier transform of d squared by over d dt squared. In fact, you know what, let's do it for any derivative, not just the second. So if we have the nth derivative of f of t, this is equal to the quantity j to the omega raised to the power n. Times the Fourier transform of f of t, such that it's equal to j omega raised to the nth power of f hat of omega. Okay, so we'll briefly talk about Parseval's theorem, then we're going to look at convolution. And convolution is a really important one because it pops out when we deal with the wavelet transform. But starting with Parseval's theorem, this simply says that the integral from minus infinity to infinity of the absolute value or the magnitude of f hat omega, that magnitude squared d omega, this is equal to 2 pi times the integral from minus infinity to infinity of the magnitude of f of t, that magnitude squared, dt. And what this basically says is that the amount of energy in the signal in the frequency domain is equivalent to the amount of energy in the signal in the time domain. Meaning that you can calculate the total energy in the signal in either of those domains and you'll get the same result. This theorem is useful when we look at the inverse wavelet decomposition, which relies on this theorem in a way to preserve energies when you do the decomposition with that method, which we're like 2 weeks away from looking at roughly. All right, let's talk about convolution here. So if we're going to consider the convolution of g, t, and f of t, we'll write this as f star g, which is not still a function of t, is equal to the integral from minus infinity to infinity of f of t minus tau times g tau d tau. And in this case, we're using the star as our convolution operator. So the nice thing about the convolution is that it turns out that a convolution in the time domain is equivalent to a multiplication in the frequency domain. So if you wanted to compute the convolution of two functions, you might find that it's easier to compute their Fourier transforms, multiply those, and then do an inverse Fourier transformation. Such that we can write exactly what I just said, that this convolution, f convoluted with g, is equal to this inverse Fourier transformation of f hat omega times g hat omega. And we're going to use this property later when we define the wavelet transform. And how we actually end up computing the wavelet transform is based on this convolution approach, this convolution property. Okay, with that, let's talk about what are known as frequency response functions, which are used to study the behavior of vibrating structures, typically linear structures, although people still apply this idea to nonlinear systems in terms of applying it just to their data. Whether that's a good idea or not is something that could be debated. I'm on the side that that's not a good idea. Doesn't mean people don't do it, but that's just the reality of things. Okay, so first off, the frequency response function of a vibrating structure is going to be defined as h of omega is equal to x hat of omega divided by f hat of omega, where, so x of t is, and it should not be a vector in this discussion, where x of t is just the displacement of the structure, therefore x hat omega is its Fourier transform. F of t is the applied external force, which is at this point just a generic function of time. And then f hat omega is the Fourier transform of f of t. So this is the most basic way to define a frequency response function. You can also do things using power spectral densities and cross spectral densities as well. We're just going to use the simple definition shown here. And you can do a whole bunch of different things, especially if you have multi-input, multi-output types of testing as well. All right, so in this case, the frequency response function, as defined here, has units of displacement per unit force, and it is called the receptance of the structure. You can also compute it for the velocity, in which case we'll use big Y of omega, which is then equal to, I'm going to need to move this over a little, which is equal to x dot hat omega over f hat of omega. So in this case, it's just the Fourier transform of that velocity signal, which we can use the derivative property and write this then as minus j omega x hat of omega divided by f hat of omega, which is then equal to j omega times h of omega. And in this case, the units are velocity per unit force, something like meters per second per Newton. You generally do not say meters per second Newton. You generally leave it as meters per second per Newton. And it's called the mobility of the structure. You can do it for the acceleration as well. We'll use a big A here for this. And this will be equal to x double dot hat of omega, which is the Fourier transform of the acceleration, divided by f hat of omega, which is simply equal to minus omega squared x hat of omega divided by f hat of omega, or simply equal to minus omega squared times h of omega. And typically, when you take the Fourier transform of a real signal, something I should have mentioned before, when you take the Fourier transform of a real signal, you get back a complex signal in the frequency domain. Likewise, if you had a real signal in the frequency domain and you took a Fourier transform, you get back a complex signal in the time domain. And so H here is complex. X and F hats are also always complex because we're generally dealing with real signals in the time domain. Okay, so this big A has units of acceleration per unit force, and just like the mobility, you'll write that as meters per second squared per Newton. And this is called the accelerants, or also sometimes called the inertance as well. Okay, and so when people try to study like the dynamics of structures, they do measurements, and then they'll compute these frequency response functions and study what they look like. We're going to end up doing that for a single degree of freedom, and then we're going to do an example with a multi-degree of freedom system as well. But before we do that, I also wanted to talk briefly about the inverses or the reciprocals of these frequency response functions. They also have meaning as well. First, the inverse of the receptance is going to be called the dynamic stiffness of the structure. We'll call this R of omega, and that's equal to 1 over h of omega, or in this case, it's the Fourier transform of the force divided by the Fourier transform of the displacement. The mechanical impedance is the reciprocal of the mobility. So in this case, it is simply 1 over j omega h of omega, which is equal to the Fourier transform of the force divided by Fourier transform of the velocity, or Fourier transform of the force divided by j omega times the Fourier transform of the displacement. And then lastly, the apparent mass, which we'll represent using W, capital W. This is equal to minus 1 over omega squared h of omega, which is again the Fourier transform of the force divided by the Fourier transform of that acceleration signal times the Fourier which is equal to the Fourier transform of the force divided by minus omega squared times the Fourier transform of the displacement. And you can compute frequency response functions for multiple multi-degree of freedom systems, typically using matrix formulations. We're going to see this in example 2. You can really only do this analytically for linear systems. You can do it in like terms of applying it to data. You can apply these to both nonlinear and linear systems. But whether you get something meaningful out of it will depend on for a nonlinear system, will depend on the amplitude of the response. For a linear system, you can always do that. You always get something interesting and useful. Okay. So in that case, we're now going to look at an example. So we're going to consider just a single degree of freedom harmonic oscillator, simple harmonic oscillator with both linear grounding stiffness and damping, with some force F of t applied to it and displacement x of t. In this case, the equation of motion is m x double dot plus b x dot plus kx equal to f of t. And what we want to do is determine the frequency response function for the oscillator analytically. Lost a y there. Analytically. And then we want to plot the magnitude and phase of that FRF for different parameter values. So I've already done the plotting, that's on the next page, but I would like you guys to work with your neighbors on doing part A, and then I'll walk around and answer any questions you have, and I'll also write down my solution at the same time. Okay. All right, so to compute the FRF, we're just going to take the Fourier transform of both sides of the equation of motion. We're then going to apply the linearity and derivative properties. Just to break it up, we then end up using being able to pull out this Fourier transform of x, or this x hat omega. On the right-hand side, you just get the Fourier transform of the force. We never specified what that was. It can be almost anything. And as a result, we end up with this h of omega, which is simply 1 divided by the quantity minus m omega squared plus j b omega plus k. And then I've gone ahead and plotted this for you on the next page. So the base system, or base values, the parameters I chose were m equals 1, c equals 0.01, and k equals 10. And then here I'm showing what happens when you vary k, both increase or decrease it. So first off, when we look at the frequency response function, this peak here, let's do one peak. This here is the natural frequency.
Just to make sure, C is the damping ratio, or damping coefficient.
Yeah.
Okay.
Yeah, we're using B. Okay, we use
Word,
B.
but
Yeah.
it makes sense
Yeah.
now.
C or B, both are the same. Yeah, sorry. So the peak, is the natural frequency. I labeled one, so in this case, that's natural frequency, that's natural frequency, that is natural frequency. All of these peaks are the natural frequency. And if you recall the resonance phenomena, when you force set the natural frequency, you get the highest amplitude. You get a very large amplitude at least. And so in this case, when we increase K, we increase that natural frequency, so we get this kind of behavior. When we decrease K, we end up decreasing that natural frequency. That is for decreasing K. Beneath that is plotted the phase of this response. And then the key thing I want to point out here is that the phase will go through pi over 2, whether it's minus pi over 2 or positive pi over 2. When you go through a resonance peak, the phase will decrease by pi, and at wherever that pi over 2 is, we end up, that's the natural frequency. So in this case, it's minus 2 pi at the natural frequency. So one thing you can do when you're looking at an experimental signal, if you want to get very accurate natural frequencies, you can look at the phase and determine when it's minus pi over 2 and do an interpolation, which is much more accurate than doing an extrapolation on the magnitude, and use that to determine your natural frequency. So in this case, when we decrease K, we're shifting the phase backwards. And we increase it when we shift the phase to the right when we increase K. For M, we have an inverse behavior. So when we are varying M, increasing M will decrease the natural frequency. Increasing M or decreasing M will increase the natural frequency. And again, natural frequency is square root of K over M. So that should make sense for us. Still, all of these peaks are the actual natural frequency of this oscillator. In this direction, this is our increasing M direction. And then decreasing M is in this direction. One other thing I wanted to point out is that at omega equals 0, this is the response under a static force. Okay, and if we vary the damping C or B if you want, if we vary that damping, it does not shift the resonance peak. Well, it does, but very slightly compared to the stiffness or damping. And in this case, I've only done increasing C simply because decreasing it just makes that peak get very much sharper. And one thing you'll note is that the peak is here, 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 and then it will slowly start to shift as we increase that damping. And again, this is for the phase, it tends to flatten it out for increasing C. But you can see that they're still all intersecting 2 pi over here, roughly. Slight shift, actually. All right. So the MATLAB codes for how I created this are over down here, if you ever wanted to use them. We're now going to take a look at a 3-degree of freedom system. Shown here, we can do very much the same as what we did for that single degree of freedom, now using matrix approaches. In this case, I've already started to write out the equations of motion in this big matrix form, which we will condense down to m x double dot plus bx dot plus kx is equal to forcing vector f of t. One thing you should note is that none of these equations are nonlinear, and that's because you can't do this for nonlinear systems. You just can't. You can take the Fourier transform of a polynomial under very particular conditions, which you then need to specify, which we're not going to do. Okay, so again, we're going to determine the FRF analytically for this system, and then we're going to plot the FRF for some parameters. I've done the plotting part, but you guys work on the analytical part and see what you can do with that.
So like each
All right, so we had our equation of motion there. To compute the FRF, we're going to use this vector equation or matrix form, equation 37. We'll take the Fourier transform of both sides. The Fourier transform applies equally to matrices and vectors. So we use our derivative property and the linearity property. We end up with almost exactly what we had in the previous example, except we have matrices instead of scalars for the mass, damping, and stiffness. Here we're going to note that the displacement is equal to the frequency response function. You can think of it as also like a transfer function. Though we call it a frequency response function, they're the same thing. The frequency response function multiplied by the force, the Fourier transform of the force, meaning that if you, for any f hat omega, we can compute the displacement response given this transfer function. That means that when we go and compute like an f of t or a fast Fourier transform of a response and compute this f or f using measurements, we are effectively learning the dynamics of the system. So then this f or f is very much the same as what we had previously, except that we have to take an inverse rather than dividing by it. Okay, so I'm going to plot on this next page so first off, this frequency response function is a matrix. It will have entries. It's going to be a 3x3 matrix in this case. And here, Hij is equivalent to the ith displacement, the frequency response function of the ith displacement with respect to the jth forcing. Meaning that if we come back up here, the first row of our frequency response matrix will be the frequency response function of that first degree of freedom with respect to each of those three forces. And then the second row will be the f or f of the second degree of freedom with respect to those three forces, and so on. And then this extends to n degree of freedom as well. Okay, so this is just the plot of the receptance and the phase for the f or f of 1 with those three components shown there. And then each peak here represents one of the three natural frequencies. In general, we also have what are known as zeros in this case. And so like this point here is effectively, well, a minimum of the response. Without damping, it's actually a 0 in the response. You get a 0 amplitude at this degree of freedom for this if you forced at this frequency. All right. So what it looks like for the second degree of freedom, and these omegas got shifted a little bit. Here's what it looks like for the third degree of freedom, and then if you compute the f or f for x1 with respect to f3 and then x3 with respect to f1, you find that they're exactly the same, and the reason is because of what is known as reciprocity, or reciprocity theorem. Okay, so MATLAB code is given here, and then we'll start the discrete Fourier transform next week.